Okay, next we're going to talk about probability distributions for discrete random variables. And to help set this up for us, let's take a look at this diagram that we saw at the very beginning of the course. So just to review, we have this population of items or objects, and it's very, very large. It's hard to get at every single item. One thing about this population that we might be interested in is a numerical summary measure called a parameter. In this case, I drew out the Greek letter mu for the population mean. So again, since all items are so difficult to get at in the population, what we do is we try to take a representative sample of those items. And the sample now consists of a smaller set of items that are much easier to work with. Again, in the sample, we might calculate a numerical summary measure called statistic, perhaps, for example, the sample mean. And then using this information that we have in the sample, we try to draw inferences back to what's going on in the population. Now, with respect to this population, we're going to want to start characterizing it with what are called probability distributions. And what these probability distributions represent is basically how items are distributed, at least in the like a numerical sense, in terms of what the actual characteristic values are, such as GPA values. We're going to look at how those GPAs, let's say, are distributed. Do we have a lot of them that are between 3.5 and 4.0, or maybe a small amount? And we characterize how they're distributed with probabilities. So let's look at a very simple example to help explain this. Suppose we have numbers on slips of paper. So for example, here we have the number 6. We have, oops, actually that was the number 9, excuse me. We have the number 5. And we have basically slips of paper with numbers 0 through 9, the integers written on them. And what we like to be able to do is actually sample 50, repeat a sampling process 50 different times. So perhaps I have all the numbers here in this hat, and I'm going to randomly not look. I'm going to randomly select an item and not look at what I'm selecting, and this time I got a 0. Now I'm going to put this back in the hat. I shake the hat up again, and this time, oops, I accidentally looked, but let's say I didn't, and I got the number 1. And so we're going to do that 50 different times. Now, since we have just 10 numbers here, and they're all on individual slips of paper, and as long as I'm randomly selecting a number there, we can say that the probability of selecting a 0 is equal to 10%. Probability of selecting a 1 is equal to 10%. The probability of selecting a 9 is equal to 10%. And so let's actually look at how we can actually then simulate this process in R. So let me come back over here to 10. So what I'm going to do is create an object called X that's going to have the values of 0 to 9 in it. Remember that the colon in R represents the word to, T-O. And then we're going to use the sample functions for us to simulate this drawing out of a hat process to allow us to take the sample. So I say sample, and what do I want to sample out of? Well, this 0 to 9. How many do I want to sample? 50. And I want to do it with replacement, meaning this is like putting those numbers back in the hat after you draw them out. So let me go ahead and execute that code. I'm going to use the head function with it as well, so we can see the first 6 observations that we get. And we can see the first time we got a 1, the next time we got a 0, the next time we got a 5, and so on. And we can take a look at a histogram of all those values too. So I'm going to just use the hist function with set1, put a title on it, put x-axis label, and also I'm going to include a specific set of values for breaks. What this is going to allow me to do is control where those classes are formed on the x-axis. Now, what I would like you to try on your own is to see what would happen if you wouldn't specify the breaks here. And what you're going to see is one little problem that R has when dealing with discrete random variables in a relatively small sample size. By specifying these particular breaks here, everything will work out just fine. So if I hit run there, and let me find my plot. I'm actually on a different monitor. And here we go. So 5 times I got a 0. 6 times I got a 1. 5 times I got a 2. And so on in this particular sample. So this takes us to page 3. Now you might be thinking, well, wait a second. You just told me that we would expect 10% of the time to get zeros, 10% of the time to get 1s, and so on. Well, that's what's representing the probability distribution of the population. What we actually get for our sample can be a little bit different depending upon what our sample size is. Now, as we will see shortly, as that sample size grows, then what happens in the sample is going to be more representative of the population, and the proportions of times we get zeros, that we get 1s, and we get 2s in our sample is going to be much closer to what those population values are. We're going to let y denote the number selected on a draw from 0 to 9. Note that this is a capital Y. You'll see why that's important coming up. In statistics, we call something like y a random variable because it can change from, in this case, draw to draw in a random manner, which is controlled by a particular probability structure, such as I would expect 10% of the time to get zeros, 10% of the time I would expect to get 1s. And so since we have this expectation regarding y, what we can do is formally write out what's called a probability distribution for y. And this is what it looks like. So the probability that y is equal to 0 is 0.1. The probability that y is equal to 1 is equal to 0.1 as well. And you can keep on going all the way down to the last value and write out the probability y is equal to 9 is equal to 0.1. This is called a probability distribution. Now, if you notice here, I also have a lowercase y here as well. In statistics, especially when we want to define stuff formally, we always use uppercase y to represent the random variable, or I'm sorry, the uppercase letter to represent the random variable, and the lowercase letter as a way to say, hey, this is one particular value that our random variable can take on. And so that's why I have in this table here the lowercase y's. And as you can see, 0 here, 0 here. This is how the lowercase y is actually used. So for example, maybe capital Y here is a random variable denoting how many computer-like devices that you own. A person could be observed to own, let's say, 3 devices or 4 devices. A particular value of number of devices that they have. In a generic manner, this is denoted by then the lowercase version of that uppercase letter. And as I have here in red, this distinction can be difficult for students learning statistics in a formal way for the very first time, unfortunately. And what makes it even more difficult is that many introductory textbooks, such as, for example, Ott and Longnecker's textbook, will simply use lowercase or uppercase letters for both meanings in order to make it easier for students. Instead, what I like to do is actually make that distinction between uppercase and lowercase letters, because this will actually help, especially for those students who will be taking more courses later on in terms of statistics courses. Okay, so let's take a look at some notes here. So why is the term probability distribution used? Well, simply put, it shows how the probabilities are distributed for potential values of y. Now, since y can only be 0, 1, 2, all the way up to 9, then if I were to add up all those corresponding probabilities, then I get 1. Because you have to be one of those 10 different numbers. Another way we could represent this is the sum from y equals 0 to 9, of the probability that the random variable y is equal to a particular value of y is equal to 1. Of course, I don't have a way to get like a number like 4.2 on my draws. Don't have a way to get a number like 1.7 on my draw. So for all those other cases that are not listed, those corresponding probabilities are equal to 0. Now again, a probability like the probability y is equal to 7 is what we expect to have happen if the experiment's repeated an infinite number of times. In our actual sample that we had, the probability that y is equal to 7 was actually just equal to 0.04. Now there's actually two different kinds of random variables out there. One's called a discrete, one's called a continuous. We are working with a discrete random variable, and this term is used to denote when you have a random variable that has essentially a finite number of possibilities. Here we have 10 different possibilities. We will learn about continuous random variables later in this course. Now, in the sample, we saw the percentage of times that we got a 0, that we got a 1, that we got a 9. And if you were to take a larger number of samples then, what would happen? What would happen to these percentages? Well, again, we have this probability distribution that helps us make that determination. As we take a larger and larger sample, essentially our sample is becoming more representative of what's happening in the population. So if I were to use my sample function again, but now instead of using a sample size of 50, I use a sample size of 5,000 instead, look what happens. In terms of the number of times that I get a 0, I get 494 out of 5,000, which is approximately 10%. How often do I get a 1? Well, 501 times out of 5,000, that's approximately equal to 10%, and so on. So now as we have that larger sample, our sample is becoming more representative of the population, and we are getting what we expect from this probability distribution. Here's also a histogram showing how the height of these bars is becoming more uniform across the different range there. Okay, some questions. Suppose another sample of size 50 is taken. Would you expect the same observed values for the sample to be found? Well, we've already seen that earlier, and I've already answered that. Well, what if, though, you had this probability distribution instead? You know, what would happen? So this is actually on page 8. Well, again, what this probability distribution is saying is that about 1% of the time you would get a 0, 3% of the time you get a 1, and so on. It just so happens that the way that these numbers are represented or distributed is a little bit different. If we go back to our hat example here, what I could do, for example, is have maybe 100 of these slips of paper, have one that has a 0 on it, have 3 that have slips have 3 slips of paper that has the number 1 on it, and so on. And that will show you how this probability distribution would be represented in that particular case. Some characteristics of probability distributions for discrete random variables. Well, excuse me. The probability that you observe a particular value has to be always greater than or equal to 0. Again, notice this right here, that equal sign is in there. All probabilities are less than or equal to 1, and all these probabilities add up to 1. We actually saw an example of that earlier. Very often, you will hear people represent or refer to probability distributions for a discrete random variable as a probability mass function. Now you might be wondering, why are you introducing even more terminology here? Well, the reason is because this is an introductory stat course, and after you get done with this stat course, you're going to come across a number of different terminologies to mean the same thing. And so that's why I try to let you know what those terms are. So in addition to there being another set of terminology that you need to know, there's also some additional notation that you need to know. A little bit more of a formal notation associated with making these probability statements. And so with this terminology, or I'm sorry, this notation that we use with this P parentheses and parentheses, we can also define a notation that uses f of y. Now you've seen similar expressions like this with respect to, like in an algebra class. You have a function of x or you have a function of y. Well, what we can see here is that our probabilities are functions of y, our random variable, and its corresponding values that it can take on. And so the probability that our random variable y is equal to one particular value that we denote again by little y, that notation can also be represented by little f of y, a function of y. And by looking at all of possible f of y values, we form what's called a probability distribution function, or PDF for short. We will use this terminology throughout the rest of our course. So relative to our last example that we had with the 50, where we were drawing numbers from 0 to 9 50 different times, the actual probability distribution function then is represented simply like this. So f of 0 is equal to 0.1. F of 1 is equal to 0.1 as well. And again, in this particular case, it's just a different way to represent what we had before. Now, as we go along here, you will see some differences of how we use this f of y notation. But, by introducing this different notation, it's not meant to confuse you. It's to make sure that you understand how people typically denote these kinds of quantities. And there are some advantages that you will see of using this f of y notation now in a more mathematical setting. Now, just to make sure you understand this, incorrect ways to use this f of y notation is use a capital Y inside this f. Again, we use the lowercase y to basically be a placeholder for a particular value that a random variable can take on. We would also not say, let's say f of y is equal to 0 or f of y is equal to 1, similar to what we did with our probability statements. That's typically not how this notation is used. Now, with this f of y notation, again, that's our probability distribution function when we look at it across all possible values of y. We can also define another kind of function called the cumulative distribution function, or CDF for short. Again, this is going to be something that we will be using now throughout the rest of this course. And all that a CDF represents is a way for us to accumulate probabilities as our values of y increase. The formal notation associated with this is using a capital F as for our function. So capital F of y is our CDF. And in terms of our probability notation, all it represents is the probability our random variable y is less or equal to a particular value of y. So for example, with our 50 numbers examples, maybe I might be interested in what's the probability that I will draw out a number that's less than or equal to 5. Well, using the CDF notation, we can represent this as capital F of 5. Now, relating this back then to our f of y notation, what we can do is take the sum of all possible values that y can take on up to our one particular value of y that we're interested in, take the sum of these f of y's. In a more informal mathematical notation, we would say, okay, let's sum over all possible values of t that are less than or equal to y of f of t. That might be a little bit confusing at first, but I think it will be clear once we take a look at this example here. The key is to understand that this CDF function, or the CDF I should say, is just a way for us to accumulate probabilities as a function of y. So with our 50 numbers example, little f of 0 was equal to 0.1. And if I'm interested in, well, what's f of 0, a capital F of 0, in other words, the probability that y is less than or equal to 0, well, that would just simply be 0.1 as well. When our little y was equal to 1, little f of 1 is equal to 0.1, then what capital F of 1 would be now the probability that capital Y is less than or equal to 1. In other words, f of 0, little f of 0, plus little f of 1. Obviously, when we have capital letters and lowercase letters, when they mean different things, it could be confusing. So I apologize if sometimes the words don't come out of my mouth properly all the time. But I think the concept here of what we're trying to do is simple. We're now looking at ways to accumulate these probabilities. So capital F of 9 then is equal to 1, because my probability that I'm going to draw something that's 9 or less is 1, because I only have slips of paper that are numbered 0 through 9. Okay, so some questions to make sure you're familiar with this. What's capital F of 0? Well, we just saw that. But what's capital F of 1.5? Now, of course, I don't have a slip of paper that has the number 1.5 on it. I have a slip of paper that has 1. I have a slip of paper that has 2, but not 1.5. So, putting this in terms of our probability notation here, I'm looking at what's the probability that y is less than or equal to 1.5? Well, that's equal to little f of 0 plus little f of 1. I can't go up to 2. So in other words, this value is 0.2. So in other words, this CDF, I can define it for different values of y that I cannot actually observe. The key is I'm always looking at less than or equal to it. And so when I look at then the sum of which probabilities are going to be accumulated, I just make then the corresponding adjustment that I can't have 1.5. I can have 0, I can have 1. So then what's capital F of 1.9999? Well, exactly the same that we had here before. I changed this to a 1.999 and so on. And again, I'm just accumulating the two probabilities. But once I get to this capital F of 2, though, now I can have a possible value of 2 when I'm drawing these slips of paper on my hat. So capital F of 2 then is f of 0 plus f of 1 plus little f of 2. In other words, 0.3. And lastly, what's capital F of negative 1? Oh, remember, we don't have any probabilities in terms of a function of y until we get to at least 0. So that means capital F of negative 1 is equal to 0. What's capital F of, let's say, 100? Well, again, I can have numbers 0 through 9, and I'm accumulating these probabilities, so it's 1. Well, let's take a look at a plot of what this CDF function looks like. Here's what we have. Notice, as I'm less than 0 for my y, I'm at capital F of 0. I'm sorry, I'm at a capital F of whatever that number is, that's equal to then 0. But once I hit a y equal to 0, then that's when I have this jump. How much do I jump? Well, it's little f of 0, because that's what I'm now accumulating. And then we see, for example, if I was at, let's say, 0.5, notice that capital F of 0.5 is still at 0.1. It's not until I actually get to a y value of 1 do I have a jump. And now capital F of 1 is equal to 0.2. And so we see an interesting function plotted here, where it's almost like stairs. That I go up these stairs, and as I accumulate these probabilities, as I increase my y. But I don't go up to another stair until I get to a possible value of y that I can actually observe. And so anyway, so you see this as stairs. Some people actually refer, or most people actually refer to this as a step function. So I take a step up once I hit y equal 1. I take a step up once I hit y equal 2, and so on. Now this, how I actually did this plot, don't worry about that for now. Basically, I had to use a particular function here that we will talk about later in this course. So don't worry about that for now. Let's take a look at some other examples associated with discrete random variables, finding the PDF and finding the CDF associated with it. And our first example deals with the Price is Right game show, where we're going to play the game Plinko. So what Plinko is that, and I'll show you a short video in a second. Basically, we're going to have a contestant stand at the top of the Plinko board, so they're going to actually go up the stairs, and they have like a chip. You can see like a circular disc, and they're going to put this circular disc somewhere on the board, and they're going to let it drop down, and it's basically going to hit, you could say, let's say nails that are sticking out of the board, and it's going to bounce around as it's moving down. And the goal for this contestant, or this person who's going to be standing at the top of the board, is that they want this Plinko chip to eventually land right here, right above the $10,000 spot. And if it does, they win $10,000. If instead the chip lands, let's say right here instead, they win $0. So a question of interest for contestants who are on the Price is Right and play this game is, well, where should I drop this chip on the board? Should I drop it over here? Should I drop it over here? Or should I drop it in the middle? Which is going to maximize my probability of winning $10,000? So I have a short video to help demonstrate this. Let me get my video out. And we're just going to watch this one contestant drop one chip on the board. Watch as this chip is bouncing around, and you'll see what happens at the end in terms of how much money he actually wins.
Put him against the wall, drop it, 10,000 right in the middle. Good luck, man. 5 chips. Here we go, guys. They win some money. Here comes chip number 1, 10,000 in the middle, 10,000 in the middle.
So you can see people get real excited. But then again, if I won $10,000, I'd probably be excited too. Maybe not display the same excitement as him, but I would get excited. We'll watch this last one and see where it goes. You can see this time now he won $1,000. That's still something to be excited about. Anyway, let me get back to my notes here. And so where these chips actually fall correspond to probabilities. And so let's now let X be a random variable denoting the amount 1 for one chip. So X is like our Y before. You can use any letter you want to represent a random variable. Just to be different, I decided to use X instead. And there's been this paper that's actually computed the corresponding probabilities for if I were to drop the chip right in the middle of the board, meaning right above the $10,000 spot, what would be the probability that one would win $10,000? What would be the probability that they win $0? What would be the probability that they win $1,000, and so on? And so with that, then we have a PDF, probability distribution function. So if I drop it right in the middle of the board, right above the $10,000 spot, what's the probability that X, the amount that I actually win, is $10,000, is about 0.25. What's the probability that I win $0? It's about 0.41. So significantly high probability. What's the probability that the chip ends in the $100 slot? Well, it's about 0.02. And so now if I were to then drop the chip, let's say now above one of the $0 spots. So let's actually go back to our board here. Let me do a little bit of erasing. Oops. Well, for some reason I cannot erase. Let me try it one more time, and then I'll give up if it doesn't work. It's not working. That's okay. So let's actually go down here. Now, they've played the games a number of different ways. I will say that in this case, they actually played it once when there was $100,000 as the middle slot. But so this would be like dropping it above the what normally would be a $10,000 slot. But let's say instead I drop the chip here, which would be above a $0, or drop there above the 0 as well. What would be the corresponding probability distribution function for that case? Well, this paper found that. And now the probability of winning $10,000 actually goes down. Now it's only about 0.21. What's the probability of winning $0 is 0.37, and so on. So with these 5 different probability distribution functions, if you wanted to maximize your chance of winning $10,000, where should you drop the chip? Well, if we look at this entire row here, we see that the highest probability corresponds to dropping it right in the middle of the board above the $10,000 slot. That's where you should drop the chip. And that's the way most people think. I want to maximize my probability of winning that $10,000 value. If instead, let's say you want to maximize the winning of maximize your chance of winning at least some money, then we look over here. I want to minimize now the chip dropping in the $0 slot, and we can see that that probability is smallest if I were to drop it on the far extreme of the board where there's only $100. So in other words, to drop it right here or right there. Now, if you're a Price is Right fan, pay attention. If you're not, take about a 10-second break. For Price is Right fans, in computing these probability distributions, this paper assumes that when a chip hits a peg or nail on that Plinko board, it can only go to the opening to the left or to the right of that peg, and the probability of that happening is 0.5. Is this correct? Is this a correct assumption? So, if you're a Price is Right fan, think about that. And then if that assumption is wrong, what will be the ramifications? So, now, this game has been played for many, many years in The Price is Right. And so what I decided to do once was to actually record all Price is Right episodes that appeared for 1 year on the TV. And whenever the game was actually played, I kept that recording, otherwise I deleted it. I then gave that recording to one of my graduate students and had my graduate student actually watch and then record what actually happened in the game. Now, I would like to note that this graduate student was very interested in this little research project that I gave her. So I did not force her to watch The Price is Right over and over again. She wanted to do this research project. So for this one particular year, in terms of people dropping these chips, when the chip was dropped right above the $10,000 slot, 4 times that person won $10,000. 8 times they won $0, 11 times they won $1,000, and so on. And so in total, let's see now, so this 1923, 31 times it was dropped right in the middle of the board. And so if I take 4 divided by 31, I get to 0.13. So you can think of these as estimated probabilities. And so what we can do is compare these estimated probabilities to what was actually calculated in the paper as what would be, let's say, the true probabilities, or you can think of it as the population probabilities. And we can see there are some similarities and there are differences as well. Well, what causes then these, let's say, estimated probabilities to be different from those probabilities that we saw on the previous page? Well, again, this gets into the whole idea of the sampling process. You know, this was a sample of 1 year's worth of people playing the game. And so we wouldn't necessarily expect what happens as a sample to be exactly the same as what should happen. This is very similar to what we saw with drawing these these pieces of paper, number from 0 to 9, out of a hat. That for one set of draws to the next, you're going to have variability. What happens in the sample is going to change from one set of draws to the next. But if this drawing process or playing Plinko is repeated many times, you would expect then these corresponding probabilities to get very, very, very close to what we would expect to have happen in terms of like the population. So let's take a look at another example here. This deals with field goal kicking. This time our random variable, we're going to use the letter Y, is going to denote the number of successful field goals out of 5 attempts, where each attempt has the exact same probability of success. So again, think of field goal kicking. This is in football, and perhaps a field goal kicker is going to be kicking, let's say, only 40-yard field goals, so that essentially every kick is going to have exactly the same probability of being successful. And what we're interested in is, well, how many out of 5 will be successful? What's the corresponding probabilities with those? And in this particular case, we can actually use this then as our PDF, our probability distribution function. Y, the number of successful kicks, can be 0, can be 1, can all be all the way up to 5, number of successful field goals. Now, why I chose this as the PDF will be explained more later in the course. But for now, just to help you out, what we're going to see later is that this actually corresponds to what's called a binomial probability distribution. With this PDF, though, we can write out then what the corresponding probabilities would be. So let's say I'm interested in what's the probability of having 0 successes. So wherever I see a Y, I replace it with a 0. And so if I take 5 factorial over 0 factorial times 5 minus 0 factorial times 0.6 raised to the 0 power times 0.4 raised to the 5 minus 0 power. If I go through all the math, I get 0.01. So meaning that there's a low probability that there will be 0 successes. How about 1 success? Go through the math, I get 0.0768. I can do that throughout for my PDF. So we can see the highest probability case is 0.3456, corresponding to having 3 successes out of 5 trials. In terms of the CDF, well, F of 0 then would be exactly, capital F of 0 would be exactly equal to little f of 0. And then when I get to 1, so capital F of 1, then that's going to be little f of 0 plus little f of 1, and I get 0.0870. So the probability of having 1 or fewer successes would be 0.087. Capital F of 5 then would be 1, because you will have 5, 4, 3, 2, 1, or 0 successes. Okay. Well, how could I do some of these simple calculations in R? So let me come over here to using 10. In terms of doing factorials in R, I simply have the factorial function. So 5 factorial is 120. Remember, that would be 5 times 4 times 3 times 2 times 1. And then if I'm interested in, let's say, when y was equal to 2, I would need 5 factorial divided by the quantity 2 factorial times 3 factorial. I get 10. And then let's say I combine this with then those corresponding other components of the PDF. I would need to take 0.6 raised to the y power, or 2, 0.4 raised to the 5 minus y power, or 3. And so f of 2 will be 0.2304. Now, let's continue here. Let's actually put all the possible values of y into a vector. If you remember how to do that, we use the C function for combine or concatenate. I'm going to put 0 through 5 in there. Instead, if I wanted to, I could have also done this, 0:5, and that would say 0, then TO5, all integers 0 to 5. The corresponding probabilities, I can get those from what I've already written out. I actually just simply typed them in there like that. And then what I can do is I can sum up all those corresponding probabilities as well. And we can see I get 0.998, 9998. Why isn't this equal to 1? Well, there's just some rounding, that's all. And then let's do a plot of these probabilities. So on my x-axis, I'm going to put all my values of y. On my y-axis, I'm going to put all the corresponding values of little f of y. X-axis label, y-axis label. What I'm going to plot is going to be colored red. And then I'm going to use type equal h. And you'll see the effect that has after I do the plot. The plot opens up in a different window, unfortunately. And here we go. Let me actually come over here to Word so I can write on it. And so what the type equal h option does, it basically draws a line from 0 up to whatever the f of y value is. And so you can think of h as high, as an h, I-G-H. How high should I draw a line up to? And so for this particular plot then, we can see for f of 3, I'm drawing the line up to about 0.3456. So that's the plot of my PDF. Now, another way that we could actually draw this plot is what's shown here. And don't worry about being able to do this. The whole purpose of me introducing this, this other kind of plot is for some future notes coming up. And so by drawing the plot like this, and this kind of a plot is called a probability histogram, what I decided to do was, again, draw the height of the line that I had in the previous plot up to what f of y would be. But I also draw it in a way so that this bar now has a width of 1. And so that if I use the old, width times height to get an area of one of these bars here, that area corresponds to then the corresponding probability, 0.3456. And so if I wanted to, let's say, now find, the probability that 2 is less than y is less than equal to 3, which would be f of 2 plus f of 3. Of course, I could go to my table of probabilities for my PDF, or instead what I could do is just simply find the area of these bars. This concept of finding areas is going to be extremely important later on in our course. So this is why it's being introduced here. Right now, you might be thinking, why are we doing this? Trust me, a little bit later on, it will make more sense. Okay. Let's look at another example. This now deals with insurance. And insurance companies use statistics a lot. So if you've ever heard of the job of an actuary, actuaries use probabilities to make judgments about how often will they have, let's say, a claim for, let's say, that you get in a car wreck or that you're injured. How often will that occur? Actuaries use probabilities all the time to quantify those possible things that can happen. And so in this particular case, let's suppose that we're interested in the number of injury claims per month for a company. And suppose that we can model these corresponding probabilities of these injury claims by a PDF, where we're going to let x now be our random variable for the number of injury claims. And suppose that we have a very simple PDF for this particular case, 1 over x plus 1 times x plus 2. For values of x equals 0, 1, 2, and notice I don't put an upper bound there. The number of injury claims, there's not necessarily an upper bound for that. One person could have, let's say, more than one injury claim in a year. And so if I'm interested, let's say, f of 0, how would I find that? Well, take 1 over x plus, take 1 over 0 plus 1 times 0 plus 2. We get 1/2. So the probability of no claims is 0.5. The probability of one claim, f of 1, will be 1 over 1 plus 1 times 1 plus 2, which ends up being 1/6. Is that right? 3, 2, yep, 1/6. Now, x here is still a discrete random variable, even though there are an infinite number of possibilities for the same random variable. Simply the reason why this is still thought of as a discrete random variable is, notice I can't have, let's say, 1.5 injury claims. I can't have 1.1 injury claims. I can have 1, I can have 2, but I can't have anything in between. You can use the same kind of logic for between 2 and 3, between 3 and 4, and so on. And so let's now just verify that indeed that this is truly a PDF. Are all the f of x values greater than or equal to 0? Meaning, are all the probabilities greater than or equal to 0? And the answer is yes. You can take a look at your function here, plug in values of x equals 0, 1, and so on. You're going to see we're always going to be actually greater than 0. Are all the f of x values less than or equal to 1? In other words, are all the probabilities less than or equal to 1? Yes, they are. Again, you can start plugging in values here, and you can see that the maximum possible probability corresponds to 0 injury claims. And now, do all the probabilities, though, sum up to 1? So similar to what we saw before, this would be the probability x is equal to 0 plus the probability x is equal to 1 plus, you can keep on going. Do those probabilities sum to 1? Now we get a little bit more into the math involved here to actually show that. So in other words, what I need to do is find this infinite sum, the sum x equals 0 to infinity of 1 over x plus 1 times x plus 2. Now, to find this probability is actually easier to break up that stuff that's in the denominator. And I can actually break it up into two components, or two terms, 1 over x plus 1 and minus 1 over x plus 2. How do I do that? I use what's called partial fractions, which you've seen, for example, in a, which is typically taught, I should say, in a Calculus 2 course. If you're not sure why, indeed, that these two expressions here are equal to one another, just do the simple math to find a common denominator. So 1 over x plus 1 times x plus 2. Now, when I find that common denominator, I need to put x plus 2 up here. And I subtract off then an x plus 1 here. Look what happens. The x's disappear. 2 minus 1 is 1, and I get what I need. Okay, so now let's show that our expression actually does, this whole sum does actually equal to 1. So the way to do that is, notice that if I were to plug in a 0 into that first term, look what happens. I get 1 over 0 plus 1. In other words, I get a 1. So let's just simply, you could say, factor that part of the sum out. And so that now my sum starts at x equal 1. Remember, what we're trying to show is that this is equal to 1. So I got what I need. So if I can now just say this part is equal to 0, then I got it. So how do I do that? Well, let's do like a little substitution. Suppose we let a equal to x minus 1. So if a is equal to x minus 1, instead of having x minus 1 here, now I have a equals 0 there. And instead of having an x plus 1 there, now I have an a plus 2. And notice what happens. This part is exactly the same as that part. They cancel out, and that's why I'm left with simply equal to 1. Now, unfortunately, my eraser still doesn't work. Okay. Now, one little note here. I just want to make sure that this is unfortunately, since I can't erase, I can't look at this very well. Make sure in your notes that this here should be a plus sign, not a minus sign. Because I can't erase, I can't actually take a look at it. Although I do have my printed copy here. Let me just double check. Sometimes I do have typos, so you got to watch out for those. And at least in my printed copy, this does look like a plus. Good. Now, to do this, of course, you needed, it took a little bit of math. Now, one thing that I plan on doing in this course is to look at mathematical software that can do the math for us. And so I put an example here using Sage about how this software package can automatically show that indeed that the sum is equal to 1. We will look at Sage a little bit later in our course. Now in R, we can actually show that this sum is at least close to 1. We can't do it completely. And so let me actually go into R to show you that. And so let's let x then be, let's say, 0 to 100. Now again, 0 to infinity is what x can be, but we're going to cut it off at 100 because this is going to get close enough to infinity for us. So x is going to get 0 to 100. So if I just type x, there we go. Again, that colon means the word TO. And if I wanted to, I could find the little f of x values for every single possible value of x. So the way that R is going to react then is going to do the math one value of x at a time. And so if I type now f of x, here are all the possible f of x values. So again, when x was 0, we get 1/2. When x is equal to 1, we get 1/6. Now there's a nice little function R called cum sum, which does cumulative sums. So if I accumulate all the values of fx, what's going to happen? Well, I get capital F of 0, I get capital F of 1, I get capital F of 2. All it's doing is just accumulating these corresponding probabilities as it makes its way through all the elements of this what's called vector in R. And so I can then use the data.frame function to put all these components together so I can nicely display it. And here we go. Excuse me. So as we saw before, when x was equal to 0, little f of x was 0.5. Capital F of x is 0.5. And you can see for this CDF column here, capital F of x, you can see how it's accumulating the elements in this second column for little f of x as it goes along. And once we get it to about x equal 100, capital F of x is fairly close to 1. Okay. Come back over here to Word. So now using this PDF, using the CDF, we might be interested in finding corresponding probabilities. So in our particular case here, let's say I want the probability of having more than one claim. In other words, the probability x is greater than 1. Now since x is a discrete random variable, this would be then equivalent to the probability x is greater than or equal to 2. Because of how our random variable is defined, meaning there's an infinite number of possibilities for it, to find this corresponding probability, it's actually going to be easier to look at 1 minus the probability x is less than 2. Where does this come from? Well, this comes from using the complement that we saw before. So the probability, let's say suppose A is this x greater than or equal to 2. The probability of A is equal to 1 minus the probability of A complement, or A bar, that we saw before. And that's essentially what I did here. What's the opposite of x being greater than or equal to 2? Well, x less than 2. Again, since we have a discrete random variable here, x less than 2 is equivalent to x less than or equal to 1 in terms of these probabilities. So I can find the 1 minus the probability x is less than or equal to 1. In other words, the probability x is equal to 0, probability x is equal to 1, or little f is 0, little f of 1. And if you keep on going, you get 1/3. So the probability of having more than one claim is 1/3. Again here, notice it's more than one. So you've got to be very careful here that you don't put x greater than or equal to 1. You don't have the equal part there. In terms of the CDF, you can see how things can be rather simple. For our CDF, again, we're looking at cumulative probabilities. So if I look at capital F of 1, that's equal to the probability x is less than or equal to 1. And so when I look at probability x is greater than 1, use the complement, 1 minus the probability x is less than or equal to 1. Oh, now that's 1 minus capital F of 1. Or in other words, 1 minus 2/3 equal to 1/3. Okay. Now, would having 20 or more claims during a month seem unusual? I want you to go through the math on your own, and I will focus on the final result, which is about 0.05. So only about a 5% chance of having 20 or more claims. So that it is kind of unusual to have that occur. Now, one of the reasons why I picked this particular example is that during this course, we will actually often be focused on what's an unusual thing to occur. What's an unusual probability? And when we see an unusual thing occur, that's going to be a signal to us to make a certain kind of conclusion. And so that's why I wanted to focus on this particular example. So if 20 or more claims do actually occur for this company, you might be thinking, wait a second, there might be something weird going on here. Maybe this company is submitting false injury claims, perhaps. Or maybe some other weird things happen that's causing this unusual thing to occur. Again, as we go through the semester, excuse me, we're going to be looking at unusual events, and we quantify the unusual events through or making decisions if something's unusual by looking at probabilities. Okay. Now, one final note here. There are many special probability distributions out there for discrete random variables, and we're going to be looking at some of these special probability distributions that occur realistically in real life, you could say, throughout this semester. So with that, then, that concludes in this introduction to probability distributions for discrete random variables.